Right, I'm going to run through the examples for the systematic naming of branched alkanes in the booklet. What I'm going to do is run through these examples with you, and then you'll have more practice to do from your blue higher chemistry question booklets. So we've got a series of steps for naming branched alkanes. It looks quite complicated. And actually, I'll just remind you as well what I mean by a branched alkane. So your normal alkanes, your ones that you've just written down the names and the formulas for methane up to octane, they would be what we call straight alkanes, where we have all of the carbon atoms connected in one linear chain. A branched alkane would just be if we replace one of these hydrogen atoms with another carbon atom. So what we end up with is a chain of carbon atoms, but then another carbon atom, a branch coming off that chain. Just think of it as like a tree with a branch coming off. So, like I say, the naming rules look a little bit complicated. I hope you've read through them, because I'm not going to read through them individually. I'm just going to talk through them as I go through the first example. Okay, so we'll start with the molecular formula. So we've got this structure, this full structural formula here. So remember, the full structural formula shows all of the atoms in the molecule and how each of them are connected. And what we'll start with is just doing the molecular formula for this full structural formula. You might have been able to do that already yourself. So remember, the molecular formula just shows the total number of each type of atom. So all we have to do is count up the atoms. So we've got 1, 2, 3, 4, 5, 6 carbon atoms. So this is C6. Now, because this is an alkane, I can actually work out from the general formula. If I remember that alkanes are CnH2n plus 2, I can work out that this should be C6H 2 times 6, which is 12, plus 2, which is 14. I'm just going to double check though by counting the hydrogen atoms. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, fab. So that's my molecular formula for this structure here. Okay, now let's look at the name. So the first thing we've got to do when we're naming is find the longest continuous carbon chain. We call that the main chain or the parent chain. So to do that, you might want to start at any different end of the molecule and then just trace your pen or pencil along and try and find the longest chain of carbons you can. So if I start here, I've got 1, 2, 3, 4 carbons in a chain. If I start here and then go up this way, I've got 1, 2, 3, 4 in a chain. If I start here and go back, I've obviously got 1, 2, 3, 4. If I start here and go 1, 2, 3 around the corner, I've got 1, 2, 3, 4, 5. And again, if I start at this top corner here, I've got 1, 2, 3, 4, 1, 2, 3, 4, 5. So what I've got is I've got 5 carbons in my main chain, and it might be useful for you to circle them, what you call when you found the main chain. So your main chain isn't always the one going across the page. Sometimes it can go round a corner. And remember, that's just because when we draw these structures, even though they look very rigid on paper, these structures are flexible. So what I've made is actually the model of the structure on the paper there. And each one of these single carbon-to-carbon bonds can twirl around. So whilst the one on the paper, I think it looks a bit like this, where we've got 4 carbons in a chain and then 2 at the top. But just by twisting that molecule around, I can make it into lots of different configurations. So when you see these representations on paper, remember that these represent 3D structures that can twist around. Okay, so we've found the longest continuous carbon chain, and we're going to number the carbons in the main chain starting with the end nearest a branch. Really what we're trying to do is make sure that the branch is on the lowest possible number. So I could start here, I could say 1, 2, 3, 4, 5, or I could start here, 1, 2, 3, 4, 5. Either way, my branch is going to be on number 3. So I'm going to start here, 1, 2, 3, 4, 5. And again, I think it's useful to annotate your diagram with the numbers for each carbon. Okay, so the fact that we've got 5 carbon atoms means that the main chain is going to be called pentane. And I'm also going to have to name and identify the name and the position of the branches. So this branch here has 1 carbon atom in it. If there's 1 carbon in the branch, it's called a methyl group. Okay, so we've only got one branch, it's a methyl branch, and the main chain is pentane. So when I write the name of the compound, I write the branches in alphabetical order, there's only one so it doesn't matter, followed by the name of the main chain. And I use prefixes di, tri, etc. if there are several groups of the same kind. Well, again, I've only got one group, so it doesn't matter. I use commas to separate the numbers and dashes between letters and numbers, and there are no spaces in the name. So let's put this all together. I've got a methyl group on branch number 3, on carbon number 3 of the main chain. So I'm going to call this one 3-methyl. You can say methyl or methyl, I don't really mind. 3-methyl pentane. So remember, there's no spaces. The name and position of the branch go at the start of the name, and the name of the main chain goes at the back. I'm just going to scribble that out there. Okay, so now we're going to do the shortened structural formula. So remember, the shortened structural formula is like a condensed version of the full structural formula. It's easier to type if you were to do this on a computer. So when we do the shortened structural formula, we take each carbon in turn and we write down what it's connected to. Sounds fairly easy. It is pretty easy. We'll just explain a little bit more detail when we get to the branch. So we're going to start, let's start at the end that we've called number 1. So number 1 carbon is attached to 3 hydrogens. So I'm just going to call that CH3. Number 2 is attached to 2 hydrogens. I'm going to call that CH2. Number 3 carbon is connected to 1 hydrogen, and then it's also got this branch here. So I'm going to write CH, and then I'm going to put the branch in brackets. And the branch has a 1 carbon and 3 hydrogens. It's a methyl branch, so it's called it's going to be given CH3 in brackets. Then I'm going to continue to carbon 4 in the main chain. That's CH2. And carbon 5, CH3 as well. Okay, right, let's move on to the second example. Okay, so this one again, first thing is going to be to identify the longest continuous carbon chain. We'll start with the name this time, and if you want to, you can pause the video just now and see if you can do the name, molecular formula and shortened structural formula. Okay, so this is just me now going over the name, molecular formula and shortened structural formula, or if you want to, you can just follow along with me and we'll do them together. So to name this, we're going to find the longest continuous chain first. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. So my longest chain here is definitely going to be 4 carbon atoms, and it doesn't really matter whether I go around the corner or not, but it's easier, if it doesn't make any difference, to just call this one that's going right across the middle my longest chain here. Okay, and then I'm going to number the carbon atoms starting with the end nearest the branch. Now, what we notice here in this case is that we've actually got 2 branches, one here and one here. If I had called the main chain, if I had said that the main chain went round the corner, I would still actually have 2 branches. So if I had made my main chain go round the corner here, then I would still have 2 branches with 1 carbon in them, so it doesn't really make any difference. Okay, so starting with the end nearest the branches, to give the branches the lowest number, I'm going to go 1, 2, 3, 4. And then this time, when I put the name together, I'm going to have 2 branches, and their 2 branches are of the same type. So the branch has 1 carbon in each branch has 1 carbon in it. So there's 2 methyl branches. So I'm going to start by naming the branches dimethyl. Both branches are on carbon number 2. I have to give the position for both branches though. So this is going to be 2,2-dimethyl. That's how I'm going to name the branches. Okay, so I'm writing the name of the compound with the branches first. Again, the alphabetical order doesn't make a difference because they're both methyl branches. And then I'm going to follow it by the name of the main chain. So 1, 2, 3, 4 carbons in the main chain. That means it would be named butane. Okay, so 2,2-dimethylbutane. When I look at the molecular formula, I've again got 1, 2, 3, 4, 5, 6 carbons. And again, because it's an alkane, because there's only single bonds, I should have C6H14, because it again should follow the general formula CnH2n plus 2. I'll double check though. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. C6H14. So what you'll notice with these two molecules is that they both have the same molecular formula, but different structural formulas and different names. Can you remember the word for compounds like this? Okay, hopefully what you're saying is isomers. So we'll come on to this again, but isomers are compounds with the same molecular formula, but different structural formulas. Okay, when it comes to doing the shortened structural formula for this one, it's a little bit different again. So we're going to start at the end of the chain. The first one, carbon, has 3 hydrogens. That's fine, CH3. Carbon number 2, when we look at that, it's got the 2 methyl branches. So what we're going to write here is we're just going to write C, and then we're going to do our branch in brackets. And because there are 2 of that type of branch, we can put the 2 outside the brackets, because that shows that there are 2 of this whole thing. Okay, carbon number 3, just CH2, and carbon number 4, CH3. Right, and I'll just nip on to the next part. Okay, so what we were doing before was naming based on the structure, and what we're going to look at just now is drawing a structure based on a name, probably slightly easier. So question 2 says, draw the full structural formula of 4-ethyl 2-methyl hexane. Again, if you think you're quite confident with this, what you can do is you can give this question a go yourself and pause the video and then just look over my explanation just to check that you got the right answer. Okay, so with these, when we're trying to draw the structure based on the name, I would always work backwards. So we'd start with the name of the main chain. So you need to work out which parts are the names of the branches and which parts of them are which is the name of the main chain. Well, the main chain will be the bit that ends in ane. So we've got hexane and then we've got 4-ethyl 2-methyl. That's the branches. Okay, so hexane, hex means that there are 6 carbons. So you're going to start by drawing 6 carbon atoms in a chain. 1, 2, 3, 4, 5, 6. And then we're going to add in the branches. So it doesn't really matter. You could start at this end or you could start at this end. It doesn't matter what order you number your carbons in. For some reason, I'm just in the mood to start at the right hand side here. So I'm going to go 1, 2, 3, 4, 5, 6. So it's a 2-methyl branch first. I'm kind of working backwards through the name. For me, that just makes a little bit more sense. So a 2-methyl branch means it's going to be on position number 2. And methyl means there is 1 carbon atom in the branch. So see? And I'm going to draw in all my carbons on this structure before I add into the hydrogens. Again, it just makes it a little bit easier to draw for me. Okay, so we've got a methyl branch on number 2, and then we've got another branch on carbon number 4. So 1, 2, 3, 4. And this time the branch is an ethyl branch. So how many carbons are going to be in the branch? Hopefully you've done 2. So again, you could do this either side of the carbon atom, because remember, these bonds are flexible, these molecules can twist around. I think I've got a little bit more space underneath, so I'm going to do the ethyl branch underneath. Okay, so I've got 2 carbons in here. Now I'm just going to add in all my hydrogens. I have to really pay close attention when I'm doing this to make sure I don't miss any out, because you will lose marks in an exam if you miss out hydrogens. And how do I know how many hydrogens to add? Well, hopefully you've remembered, because carbon can form 4 bonds, all I'm doing is I'm making sure each carbon has 4 bonds. If it's not joined onto another carbon, it must be joined onto a hydrogen. So that's what I'm doing here. I'm just giving each carbon 4 bonds and making it connect up to hydrogens if it's not joined onto a carbon already. Okay, fab. Now, If you're in an exam, there's one last little check that you can do. It's a wee bit time consuming, but you could, as a double check that you've done the structure right, you could count the carbons. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. So C9. If this is an alkane, which is there's no double bonds, then I should have 2 times 9, which is 18, plus 2, which is 20 hydrogens. And you can just double check that you've got the right number of hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Oh, I think I've lost count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So that is correct. Like you see, it's a little bit of a complicated way of doing it, but it might be helpful. Okay, and then we're going to write the shortened structural formula for the compound that we've just drawn for ethyl 2-methylhexane. Again, this is probably easiest done from one of these ends here. So I'll actually do it starting at the left-hand side this time. Doesn't matter which way round you do. So we've got a CH3, then we've got CH2, then we've got a C with an H, and then we've got this ethyl branch. So to do the ethyl branch, there are a couple of different things you can do. What I'm going to do is just write the shortened structural formula for the ethyl branch in brackets. So to do the ethyl branch, I'm going to write CH2, CH3 in brackets there. And then I'm going to move on to this one, CH2, this one here, C with an H, and then a methyl branch, which remember the branch goes in brackets. And then our final CH3 at the end. If I'd started at this end, I would have a slightly different shortened structural formula, so this would also be correct. So I could have CH3, and then I would have my CH, CH3, CH2, and then I would have my carbon with my ethyl branch on it, so CH, CH2, CH3, and then I'll have this one here, CH2, and then I'll have my final CH3 at the end. I don't know why my writing's gone so squinter, but hopefully you can see that okay. Something that you could see potentially for an ethyl branch instead of CH2, CH3 would be that you could see C2H5, but I would say it's better in a shortened structural formula to write out the proper C2H3. CH2CH3. Okay, we're going to move on now and look at alkenes. So your notes say alkenes are hydrocarbons which contain a carbon-to-carbon double bond. So I've got an alkene here. We can see that there are 2 bonds connecting the carbons, so a double carbon-to-carbon bond. The double bond means that alkenes can undergo addition reactions. So having a double bond in a hydrocarbon molecule means that that double bond can break, and we can then add more atoms onto this structure. That's what we mean by an addition reaction, and we'll look at them in a minute. So the double bond means alkenes can undergo addition reactions, and compounds containing a carbon-to-carbon double bond are described as, well, you should have remembered that alkanes, which only contain single bonds, are described as saturated because you can't add anything on, but because you can add something on to alkenes with carbon-to-carbon double bonds, they are described as unsaturated. Okay, and it's in the next sentence as well. So unsaturated compounds quickly decolorize bromine solution. I'll maybe put a wee link in the notes somewhere so that you can look at that experiment. But basically what you do is you get a wee test tube with your alkene or your unsaturated hydrocarbon, and you just add a couple of drops of bromine solution using a pipette. So it's as simple as that. You can just do this reaction in a test tube and the bromine water changes from brown to colourless. We did do this experiment at National 5, you might remember it. Okay, so the first two alkenes are ethene and propene. Remember, the prefix, just like with alkanes, tells you the number of carbon atoms. So we've got eth, which means how many? 2, hopefully, and prop means 3 carbon atoms. So ethene I've got here, which contains 2 carbon atoms, and propene I've got here, which contains 3 carbon atoms. And the ene ending means that it contains a carbon-to-carbon double bond. So now you can go ahead and fill in the table with the name and molecular formula for the first 2 alkenes. So remember, we've got ethene here and propene here. Okay, so ethene has the molecular formula. Well, we've got here 1, 2 carbons, and there are 1, 2, 3, 4 hydrogens. Propene, when we look at it, I'm going to show you the structure here. This is made with molymods, and we'll draw the full structural formula in as well. So we've got 3 carbon atoms in a row, and the way I've got it here, we've got the double bond on this side, but you could draw it either way up. Okay, so on this carbon without the double bond, I've got 3 hydrogens. On this middle carbon here, because carbon can only form 4 bonds, 2 of the bonds are used making the double bonds to this end carbon, and 1 bond is used to make a single bond to this chain here, so it can only have 1 hydrogen attached. And then this end carbon, again, 2 of its bonds are used to make the double bond to the middle carbon. Carbon can have 4 bonds, so we can have 2 hydrogens on the end of this chain. Notice how I do draw the angle as it is in the structure here, on the shortened structural formula. It doesn't, in the full structural formula, it doesn't really matter. I could draw them straight up and down if I wanted to, but I prefer to draw it the way it is with the molymods. Okay, so the molecular formula for propene, 1, 2, 3 carbons, 1, 2, 3, 4, 5, 6 hydrogens, so C3H6. When it comes to drawing the shortened structural formula, again, we just take each carbon at a time. So this one, we've got a carbon with 2 hydrogens, CH2, and another one with CH2. For propene, we've got CH3 at the end here. Then we've got a carbon with just 1 hydrogen. And then we've got a carbon with 2 hydrogens. Now, you should be able to recognise from a shortened structural formula like this that there must be a double bond between these 2 carbons because they don't have quite the right number of hydrogens for making 4 bonds. Okay, and then the general formula for the alkenes, well, we need to look at what we do to the number of carbons to get the number of hydrogens. CNH. How do these numbers relate? Hopefully you can see, or you can remember it, that there are twice the number of hydrogen atoms compared to carbon atoms in alkenes, so it's CnH2n. Okay, page 7. Okay, so we're just going to look at one example for the systematic naming of branched alkenes, because it's fairly similar to the naming of alkanes, which we've already been through. So the only difference really is that when we're finding and naming the longest continuous carbon chain, that chain must contain the double bonds. So if you've got a longer chain but it doesn't contain the double bond in a molecule with a double bond, that can't be the main chain. Okay, and then the other difference is that we're going to number the carbon atoms starting with the end nearest the double bond. So I would say it's a little bit easier than with alkanes because as soon as you find the double bond, you know how to start numbering your carbons. Okay. So looking at this one, we've got our full structural formula here. We're going to work out the molecular formula first and then do the name. So I've got 1, 2, 3, 4, 5 carbon atoms. Now, using the general formula, CnH2n, I should have 10 hydrogen atoms if I've got 5 carbons. I'll just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect, C5H. Oops. H10. Okay, so let's do the name. So we're going to find the longest chain that has the double bond in it. So we're going to start with the double bond. I've got 1, 2, 3, 4 carbons if I go across there, and 4 carbons if I go around the corner. So you can circle the longest chain if you want to help you. Doesn't matter if it went around the corner, but because it doesn't make any difference, it's easiest to go across. And then we're going to number the carbons starting at the end nearest the double bond. So remember, you always start at the end. We never start in the middle of a chain with numbering. So 1, 2, 3, 4. Okay, then I'm going to identify the name and position of the branches. So I've got a branch on carbon number 3. It has 1 carbon atom in it, so it's going to be what type of branch? Hopefully a methyl branch is what you're thinking of, or methyl. And it's at position number 3. There's only 1 branch, so this is 3-methyl. And then the end of my name is based on the number of carbons in the main chain. But because I have this double bond, I need to remember to change the ending to -ine. So, and actually, I've forgotten one other step. I need to change the ending to -ine, and I also need to give a position to the double bond. So the double bond, we give the position of the lowest carbon that it's attached to. So this double bond, the lowest number that it's attached to is number 1. So as well as having 4 carbons, this chain has a double bond at position number 1. So 4 carbons means we're going to call it bute. The double bond is at position number 1. We put that in the middle of the name, and then we give it the ending -ine to tell us that it has a double bond. So this carbon here, hydrocarbon here, is 3-methyl-bute-1-ene. Notice how I'm using dashes to separate the numbers from the letters and so that it's all one word, although it has gone over the line a little bit here. Okay, then the shortened structural formula for this, taking each carbon at a time, we've got CH3, carbon with a hydrogen and then a branch, so CH, we put the branch in brackets, another carbon, this time just with 1 hydrogen, and then CH2 at the end here. So again, these carbons don't have their full number of hydrogens for forming 4 bonds, so we know there must be a double carbon-to-carbon bond in here if we see something like this, CH2. Okay. Next section is on addition reactions. An addition reaction is one in which 2 molecules combine to form a single molecule, so you do need to know that definition here. And alkenes undergo addition reactions with different types of molecules, so they can undergo addition reactions with hydrogen, forming alkanes, and this is known as hydrogenation. They can undergo addition reactions with halogens. What are the halogens again? Remember, halogens are group 7, so fluorine, bromine, chlorine, and iodine. Okay, and they're all diatomics. And when alkenes react with halogens, they form dihaloalkanes. We'll look at an example in a minute. And with water forming alcohols, addition of water, think about it as having a drink. It's known as hydration. Okay, so just look at a couple of examples now. Okay, so we're going to look at the addition of bromine to ethene. So I've got my ethene here and I've got bromine here. I'm going to start by drawing the full structural formula for both. So ethene just like that, and then bromine. The greens could represent any halogen though. And what happens when ethene reacts with bromine? Remember, the double bond can break. The bond within the halogen molecule also breaks. And then in this addition reaction, the 2 original molecules are going to combine to make a single molecule. So 1 halogen atom can add on to each carbon of the double bond. So we've ended up going from an unsaturated hydrocarbon with a double bond to a saturated hydrocarbon with a single bond, and this is actually a saturated dihaloalkane because there are 2 halogen atoms substituting for 2 hydrogen atoms, which would be there if this was a true alkane. So the structure that's formed, like I say, has these 2 bromine atoms which are substituting for the hydrogen atoms if this were an alkane structure. And we call this 1,2-dibromoethane. Okay, next one that we're going to look at is the addition of water to propene. So again, we'll start by drawing the structures. So we've got our propene here and a water here. Propene, just check you've only got 4 bonds around each carbon. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, good. And then we're adding on water. And what's happening here, what this is going to make, is again, we've got our hydrocarbon and we're going to break the double bond. We also have to break up the water molecule. We only have to break one of the bonds in the water molecule when we do this addition reaction. So what we're going to end up with is we're going to end up with an OH part here and a hydrogen atom on its own. Now we could add on these in 2 different ways. We could either put the hydrogen on its own in the middle and the OH at the end here, or we could swap these around and we could put the OH in the middle and add on the hydrogen atom at the end here. So there's actually 2 possible products with this addition reaction. So just because it's easier, I'll put the hydrogen on here and the OH on the carbon at the end there. But we're going to draw both possible structures. Okay, so we could have had the OH in the middle. And we can also have an OH at the end. Okay, the names of these, we are going to look at alcohols in a little minute, but just so that you've got them, this one is called propan-2-ol. Notice how it changes to -an from -ene because we now have only single bonds, and this is propan-1-ol because the group here is at the end. Can you remember the name of this group? You might have said hydroxyl group if you did well remembered. Okay, last little bit for this video then that we're going to look at is we're going to look at homologous series and isomers. I've given you the definitions in your notes here. You really do need to make sure you know the definitions of these 2 key terms. So a homologous series is a family of compounds with the same general formula. So for example, CnH2n+2. Similar chemical properties and showing a gradual trend in physical properties. Examples include the alkanes and the alkenes. Isomers, don't get those mixed up with isotopes. Isomers are compounds with the same molecular formula but different structural formulae. So we've already seen some examples of that when we looked at the alkanes section. Isomers usually have different physical properties. They may belong to the same homologous series or to different homologous series. So at higher, we will look in a tiny bit more detail at the fact that sometimes isomers have different physical properties. That's why it's important to be able to distinguish between them. But they might be very similar, but they might have different physical properties, but they might also belong to different homologous series. So that might mean they would have completely different chemical properties as well. So just because 2 things have the same molecular formula doesn't necessarily mean that they are similar in terms of their chemistry. Okay, so example 1 here says draw pentane and then draw and name its 2 isomers. So I'm going to start off by drawing pentane. So pent means it has 5 carbons. Okay, so here is the moly mod for pentane, and to make an isomer of pentane, remember it's got the same molecular formula, so I can't get rid of any atoms. All I can do is change the way the atoms are connected. To make an isomer of a straight chain molecule like this, the simplest thing to do would be to take a carbon off the end and swap it with one of the hydrogens on one of the carbons in the middle of the chain. Okay, so you can see now I have 4 carbon atoms in a chain, and I've got a branch coming from one of the middle carbon atoms. Okay, I'll let you think about what the other possible option could be. Remember that this molecule here is exactly the same as this one here, so when you're doing isomers it can be easy to get confused and try and draw them just by bending the molecule in a different way. That might look different on paper, but it's still exactly the same as this one here. So I'm going to draw this one on paper, and then once I've done that you can pause and see if you can come up with the third isomer of pentane. Okay, so I had 4 carbons in a chain with a branch. Notice that, like I say, it doesn't matter whether I put the branch on this one or this one, because it's still going to be the same molecule. Drawing the carbon on this one here is exactly the same as drawing it here, because I could just flip the molecule over and then it would be on the second one in. Okay, see if you can come up with the third structure. Right, hopefully what you've come up with then is that we could also take this carbon off the end and put it on this one here. So we would end up with 3 carbons in a row and 2 branches. Okay, I'm going to let you name these 2 isomers now. So this one is just ordinary pentane. And I'll let you name these 2 isomers now. Pause the video. Okay, hopefully you have named this one. Got a branch with 1 carbon on carbon number 2, so it's 2-methyl butane. And then this one, the longest chain is 3 carbons, whichever way we go, so the name is based on propane, and there are 2 methyl branches, 1 on each side with 1 carbon. They're both on carbon number 2, so this one's 2,2-dimethyl propane. Okay, next example then. Draw the compound below and then draw and name its 4 isomers. So this compound here, we haven't actually looked at this, but this is a revision from National 5 as well. We've got 4 carbon atoms that go round in a circle. This compound here is therefore called cyclo. It's a cycloalkane, and there are 4 carbons, so it's going to be called cyclobutane. And something that's going to help you to draw the isomers is to just work out the molecular formula of this compound here. So C4, we've got 4 carbons and 1, 2, 3, 4, 5, 6, 7, 8. C4H8. So all of our isomers are going to have this formula. Now, what do you notice about this formula? Well, maybe you've noticed that there's twice the number of hydrogens compared to carbons. So this is CnH2n. So our cycloalkanes have the same general formula as the alkenes. So a cycloalkane is an isomer of the corresponding alkene. So cyclobutane is an isomer of butene. With butene, there are a few different things that we can do to make it different isomers, but I'm going to start with just drawing butene with 4 carbons here. And again, remember, I'm just making up the number of hydrogens so that each carbon has 4 bonds. So I've said butene, but actually I've got to be a little bit more specific with butene, because I have to specify the position of the double bond. There are 2 possible places for the double bond to go. It could go at the end here, or it could go in the middle. This one's at the end, so we're going to give this carbon number 1, 2, 3 and 4. So this one would be called but1-ene. No branches, but there is a different options for the double bond, so I have to specify but1-ene. Okay, what other isomers do you think you could have then of cyclobutane? I've said there are 4 altogether. Okay, pause the video and see if you can come up with them. Right, so here we go, here are the others. We could, one of the simplest isomers of but1-ene would just be to do but2-ene. So here, what I've done is I've just changed the position of the double bond. If you check these, they should all still be C4H8, because isomers have the same molecular formula, but they have different structures and therefore different names. So 1, 2, 3, 4, I could number this either way, but either way my double bond is always going to be on carbon number 2 to carbon number 3, and we give it the lowest number, so that would be but2-ene. Okay, other things that we can do here then, we could also make this a branched alkene, so we could make it now, I was about to write a wee hydrogen on there, but that would have given this carbon too many bonds. So remember, your carbons can only have 4 bonds. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. You need to double check that. So this one has got 3 carbons in the main chain and 1 branch with 1 carbon atom in the branch. So it's a methyl branch and it's on carbon number 2. So this one is 2-methyl prop 1-ene. Now, actually, with this particular example, if we've got a methyl branch on a propene, there is only one possible option for where the branch can be. If the branch was at the end, it would be butene. If the branch was at this end, it would be butene as well. So in this particular case, there's actually only one possible option for this. So we don't technically need to put the numbers in this situation. So we could just call this methyl propene. For propene, there is no option between prop1-ene and prop2-ene. It's always going to be between the first and second. The double bond's always going to be between the first and second carbons if there are only 3 carbons in the chain. So just watch out for that one. And then finally, we're going to have another cyclic option. You might not have got this, I'll be impressed if you did. Okay. So we could have a cyclic molecule but with only 3 carbons in the ring and then another one out here. This one was tricky. And with this one we would call it, the name would be based on cyclopropane because that's the ring, and there is a branch on the cyclopropane. There's only one possible place the branch could be because we always give a branch position number 1 if there's just one branch on a cyclic ring here. So this is, we don't have to call it 1-methyl cyclopropane, because like I say, there could only be a branch at number 1 if it's methyl cyclopropane. So we're just going to call this methyl cyclopropane. Okay, so now for extra practice, you're going to do the revision questions for higher chemistry. I won't make you do all of them, so on page 33 to 35, you're going to do question 1, 2, 3 and 4, but you're only going to do part A, C and E for each of those ones. Okay, you are then going to do page 36 and do question 3 and 4 on page 36. This is page 33. hope that makes sense.